Welcome back. So far, what we've done for the method of initial rates is we've just kind of guessed it. We're like, oh, 2 times 2, 4, 2, that seems right. And that is actually perfectly okay. If you design your experiments well, where you're doubling things or tripling things, or you've got whole number ratios, it can totally work well, and it's possible to do it that way. But quite honestly, there's some people that no matter how much they think about it and try to picture it in their head, they just can't. And that's okay too. There's a mathematical way of doing initial rates. And when we do lab work, that's actually what we're going to do. We're always going to do it the mathematical way as opposed to kind of what I call the logic way, which is just the thinking about it way. So I'm going to show you the mathematical method for doing the initial rate method. And it comes, not surprisingly, from the rate laws themselves. And remember, our rate law for a reaction, A plus 2B goes to C, the rate law is going to be that rate is equal to some constant K times the concentration of A to the M times the concentration of B to the N. And our job is to find out what that M and N is by setting up our experiments, changing a thing, looking at the rates and stuff like that. So what we're going to do is we're going to say, well, every experiment has its own rate, right? It may or may not change depending on whether it's zero order, first order, second order, all the concentrations. But experiment number 1 is going to have a rate. Experiment number 1 has a concentration of A, and experiment number 1 has a concentration of B. I can also write the same thing for experiment number 2. So if I take and I write this, it doesn't want to write, there we go, rate 2 is equal to K times the concentration of A2 to the M times the concentration of B2 to the N. Clear up that A there, if it lets me. There we go. So we can write that for the second experiment. We could also write it for the third experiment too, that the rate in the third experiment is rate equals K times A in the third experiment times B to the N in the third experiment. Now, you'll notice those K's are the same. There's not a K1 and K2 because the rate constant is a constant. And so it doesn't change across experiments. And so we have that there. So what we're going to do is we're going to look at those two experiments. And if we look at experiment 1 and experiment 2, we've got A changing and we've got B not changing. So that's a great set of experiments to start with. And we could do it the thought way and be like, oh, look, we tripled A. What happened to the rate? And figure it out that way. But let's do it mathematically. And how you do it mathematically is you write out these two rate relations for the two experiments you're going to compare. And you always have to start with a set of experiments where only one thing's changed. Why? Because what we're going to do is we're going to divide these two equations, right? We're going to divide rate 1 divided by rate 2. And what does rate 1 divided by rate 2 look like? It looks like K times A1 to the M, B1 to the N. And rate 2 looks like K, A2 to the M, and B2 to the N. So we divide those two out. Now here's some fun things. K automatically cancels, right? Because we know that constant is a constant, so it automatically cancels. But then we're going to actually literally plug in the numbers from our results up there. Rate 1 was 40 molar per second, and that's going to be equal to, K is gone now, so we don't need to know K. We don't have to figure out K. A, which was 1.0 molar, and that's going to be to the M. We still don't know what M is. Now, my handwriting is not great. My little m looks a lot like my big M, but we can get it from place, right? 1.0 M is going to be molar. The exponent is going to be our little m. And then we have B at 2.0 molar, and that's to the N. And we don't know what that is. Right? Now we're going to divide that by rate 2, which was 120 molar per second. And that's equal to, now we're just going to make one set of equal to's here. If it's going to let me, which it does not seem to want to let me erase anything right now, which is very strange. Why can't I erase anything? There we go. So we're going to make one set of equals. Looks like that. On the bottom, we have our experiment number 2, which is going to be this data here. We have 3.0 molar to the M and 2.0 molar to the N. Same M, same N, because the rate law is the same, no matter whether we're talking about experiment 1, experiment 2, experiment 3. The rate law is the same. K is the same. M and N are the same. What changes is our concentrations and our rates. So we plugged in those actual numbers. Now you'll notice if you look at this equation, something else cancels out. And that is our 2.0 to the n. And if those cancel out, what are we left with? We're left with 40 over 120. I'm going to simplify that to 1 over 3. My units cancel here, so I actually just have 1 over 3. Is what? 1.0 molar to the m divided by 3.0 molar to the m. Remember, A times B to the m is the same thing as A to the m, B to the m. So we can actually take those molars out and cancel them, right? M molar to the m and molar to the m on the top and bottom. And so we actually just get 1.0 to the m divided by 3.0 to the m, which is the same thing as 1.0 over 3.0 to the m. Now, we look at that. Let me put it here on one line. 1 over 3 equals 1 over 3 to the m. Now, by inspection, most of us could figure out that that is equal to 1. M must be equal to 1 for this to be true. But let's say we couldn't figure it out. Or let's say we're doing data, we're doing a lab analysis. What would we do in that case? Well, what we're going to do is we are going to try to solve for m. And since m is an exponent, our only way to solve for m is by using a logarithm. So what we're going to do is we're actually going to take the log of both sides of this equation, which we're allowed to do, the log and the log. If you remember from our intro, we said, hey, the log of a to the b power is the same thing as b log a. It's just one of the properties of a logarithm. So I've got log of 1/3 to the m is going to be the same thing as m times the log of 1 over 3. Since we have the same thing on both sides, most people could just look at that and be like, well, m's got to be equal to 1. But hey, let's just work through this whole thing, because in cases where it's not so obvious, we are going to have to actually do the math. We're going to divide both sides by the log of 1 over 3. Just be careful about how you do this. A lot of people try to divide by the log of 3 or multiply by the log of 3. It's not quite the same thing because logs have their own math rules. But log of 1/3 is just a number, so I can divide both sides by log of 1/3. It cancels out over here. It cancels out over here. And I get 1 is equal to m. So that's the mathematical method of solving the initial rate method. Is you start with your rate equations for 2 different experiments where only one thing changed. You write out the generic form. So rate equals k times a to the m, b to the n. Then you put it specific for 2 experiments. You plug in the numbers. Something must cancel. If something doesn't cancel, you're in trouble. And then you're left with just solving one thing. And you do that using logarithms. And if you do that, you are good. Now, at the end, you might actually have a log. If you're doing this on experiment or if you're doing it on other things, you might actually have a log that you have to plug into your calculator. Make sure that if you're typing log of 1/3 on your calculator, that you've got the set of parentheses there. And you're not taking log of 1 divided by log of 3. That's different. Okay? Log of 1/3 is not the same as log of 1 over log of 3. That is not the same. So make sure you're putting that in your calculator right. All right, let's use that. Let's use our knowledge of initial rate laws to try to solve this problem. So based on the data, we're going to try to figure out the order of reaction with respect to O2. Now, I just made up this data. This is no real data or anything like that. It's just something for our show here. And so we've got C3H8, propane, going with 5 oxygens to make 3 CO2s and 4 waters. We want to know is that 0, 1st, 2nd, 3rd order in O2. So how do we do that? Well, we do it by the method of initial rates, because we know that because if you look over at the data given to you, it's initial rates. It's a good hint that you're going to use the method of initial rates. Okay, this is kind of contrived. So what do we have? We have 3 experiments. We have some initial rates. We're just trying to find O2 here. So that's your job. How are you going to find O2 using the method of initial rates? So go for it, see what you get, and we'll check in just a moment. Right, what did you come up with? Well, hopefully you either came up with, I'm going to do it the logical way, or I'm going to do it the mathematical way, or maybe you're like, hey, I'm going to try both and see if I get the same answer. Fantastic. Let's start with the logical way. I've got an experiment 1 and 2 where my propane doesn't change, but my O2 changes. Now, if I go from experiment 1 to experiment 2, it goes down by a factor of 3. And you can absolutely do the math for that in your, it's totally possible, but it's harder. Dividing by fractions isn't quite as intuitive as dividing by whole numbers. And so what I'm going to say is, instead of going from experiment 1 to experiment 3, I'm going to go from, 1 to 2. I'm going to go from experiment 2 to experiment 1. I'm going to compare them in that order. And in that case, my O2 concentration went up by a factor of 3. And what happened to my rate? And you're like, well, didn't it kind of stay about the same? It didn't, right? Because what do I have? I have 2.5 times 10 to the 5th divided by 2.8 times 10 to the 4th. And so, you just get out your calculator. Don't worry about it. It's just a number. 2.5 times 10 to the 8th divided by 2.5 times 10 to the 5th divided by 2.8 times 10 to the 4th. And what I get is my rate went up by 8.928. It's not a whole number. It's kind of a funky number. It's not very pleasant. Experimental data is never perfect. And so we might have to round. What are we going to round that to? I'm going to call that somewhere close to 9 and see if that helps me. If it doesn't help me, if I get an answer at the end that doesn't make much sense, then I might, okay, let me go check and see whether that assumption of tripling of turning it into 9 makes sense. Or maybe I'll do it the mathematical way where I just plug in exact values and it's taken care of. But what do I have? I have my concentration up by a factor of 3 and my rate up by a factor of 9. That tells me that it must be second order. And I encourage you, since you know the answer to this one, try it the mathematical method. Plug in rate 1 and rate 2 in your equations and solve for the order with respect to O2 and see if you get the same thing. Another one. Same type of reaction here. We've just got methane and oxygen to make CO2 and water. And we're looking at initial methane and initial oxygen concentrations and our initial rates. And we're trying to find the order of reaction with respect to O2. And again, I just made this up. This isn't actual real data. It's not telling us the order of O2. We're just trying to figure out how to use this method. You'll notice the numbers aren't as pretty anymore. And so you're like, well, can I use the initial rate method? And the answer is yes, you still can. You can absolutely use the initial rate method when the numbers aren't as pretty, because you'll find in experimental data, they're absolutely not pretty, right? Because experiments aren't perfect. And so you'll just get, numbers that are pretty close. But here, we can still use the initial rate method logically. We can do it mathematically either way. So go ahead and take a chance at it, see what you come up with, and we will check in soon. Okay, so we're trying to find O2, which means we need an experiment where O2 changed and nothing else did. If we look at the first experiment, we've got 0.0510 and 0.0987 from experiment 1 to 2. So my CH4 is changing quite a lot, but it looks like my O2 is changing too, right? I've got 0.0203 to 0.0199. But you'll notice that these numbers are awfully darn close to one another. Okay, it's not like it's hugely off. And so we'd actually consider, if we're doing the logical method, we'll actually consider those to be roughly the same. So in that case, could use that experiment to find the order with respect to methane, because we have methane changing and O2 not changing. So how do we find one where O2 is changing and methane's not changing? Well, let's look for an experiment set where methane isn't changing. And that's experiment 1 to experiment 3. And it's going from 0.0510 to 0.0507. That is close enough, okay? You don't have to have it perfect, exactly the same. It's almost impossible, right? You add 1 drop more of something in a solution, it's going to change the concentration in there by just a little bit, and it's okay if your data is not perfect. In fact, you can have things change by a factor of 17.34412, and it would still work. It would just probably be something you do with the mathematical method as opposed to the logical method. So there I go. I've got methane not changing. I've got oxygen changing. Now, how is that one changing? Again, rounding helps us a little. It's changing from 0.02 to 0.03. What is that? Well, it turns out it's a factor of 1.5. Okay, so 1.5, it's a little harder to do. Let's do this one using the mathematical method, because I don't really want to deal with having to figure out 1.5, because that's just too much for my brain. It's fine. The mathematical method works, the logical method works. So if we're going to use the mathematical method, we're going to write out the two forms of the rate law. Rate equals K times the concentration of methane times the concentration of oxygen. This is to the M and this is to the N, but that's for experiment number 1. And then I'm also going to look at experiment number 3 and divide the two. Rate for experiment 3 is K times methane to the M for 3 times O2 for 3. Once we've got those two things there, we're just going to plug in our numbers. We know that K is going to cancel, so we don't have to worry about that. Rate in experiment 1 is 4.7 times 10 to the 4th molar per second. In experiment 3, it's 10.5 times 10 to the 4th molar per second. And that's going to be equal to my concentration of CH4, 0.0510 to the M, 0.0203 to the N, 0.0507 to the M, and 0.0311 to the N. Now, you're like, well, those numbers aren't the same. In that last example where you did the mathematical method, those things to the M were exactly the same and they cancel, but it doesn't cancel here, right? I end up with some ratio that's to the M and that doesn't cancel. And you're right, it absolutely doesn't perfectly cancel, but we're not looking for perfect, we're looking for good enough. If you actually were to divide that out, 0.0510 divided by 0.0507, let me do that, 0.0510 divided by 0.0507, I get 1.00592, okay? Let me just say that, let's say M is huge and it's to the third order. 1.0 whatever it was to the third order is still 1.017. So even if M was this large number and these things weren't perfect, you're still only going to multiply it by about 1.01. It's not going to change your answer much. So what we do is, yes, we cancel these two. We say, hey, look, those two are close enough and they are going to cancel out. The rest of it is just math. You can type it in your calculator. Now, I personally, if I was doing this for my own work, not as an example, I would have switched the order of them. I always like to have the larger rate on top and the smaller rate on the bottom. It doesn't matter mathematically, but it just makes it a little easier on my brain. Things double, things triple, as opposed to things went down by 0.3 or whatever. That's a little harder to think about. But this is just math work. So we take 4.7, we divide by 10.5, all times 10 to the 4th, and we get 0.4476 is equal to, right, our units cancel here, 0.0203 over 0.0311 to the N. Now, I did make a mistake here. I just noticed. I'm going to chide myself for it. I forgot to put my units in here. All these guys should have had molar as a unit. So I'm going to kind of toss that in there and say, just Professor Clements. However, they do all cancel since they're all raised to the same power. So in this next step, I don't have any more units. And so what do I get? 0.0203 divided by 0.0311 is 0.0203 divided by 0.0311. And that is 0.6527 to the N. That one is a little stranger. That one you don't just look and you say, well, if N is 1, it's kind of close. I don't know. So this is a great one for the mathematical method. So we've got 0.4476 is equal to 0.6527 to the N. What we're going to do is we're going to take a log of both sides. And then we're going to take the N down. So we've got log of 0.4476 is equal to N times the log of 0.6527. I can divide both sides by my log of 0.6527 divided by log of 0.6527. And then this cancels. And I solve this and it gives me N. Just be careful when you type this in your calculator. This is not log of 0.44. Oops. 0.4476 over 0.6527. Absolutely not. That is not the same. You actually have to type log of this one, close parentheses, divided by log of that one, close parentheses. So I'm going to go ahead and do that. I've got the log of 0.4476, close parentheses, divided by the log of 0.6527, and I get n equals 1.88. Like, okay, well, I've got a reaction that's 1.88 order. If you remember back, we said these things are generally small, round, whole numbers, integers, 0, 1, 2, 3. Okay? And there's a good reason for that, which we'll see later on when we talk about mechanisms, is most of the time you have a mechanism where one thing reacts with another thing, and that ends up being kind of overall second order. So when we see n equals 1.88, we're probably not going to guess that n is actually 1.88, because it doesn't have much meaning to say that n equals 1.88. We're going to say n is 8.18 is awfully close to 2. And so we're going to call this second order with respect to O2. And that's how we're going to go ahead and do this. When we use a mathematical method, it's never going to be perfect. We're going to make assumptions. Now, if you got 1.54, you might have to stop and think. There are reactions out there that are 1.5 order. You might have to stop and think, what's the chances of me having a 1.5 order reaction? Because right, rounding 1.54, you're like, oh, that's closer to 2. It's not that much closer to 2. You're kind of split in the middle there. But when you get 1.8, when you get 1.2, you can round that to 1. If you got 0.9, you can round that to 1. Right? But if you're getting 0.4, don't round that to 1. Don't round that to 0. Think about that a little more. Does it make sense that it's 0 order or first order? Or do you have other data that you can go from as well? So we're going to say this awfully close to 2, which means it is second order in O2. So, whew, what do we have? We have rate equals K times the concentration of methane, CH4. We still don't know what that is, but we know it for O2 is going to be squared because we figured that out. Wow. Those problems take a while, don't they? Okay. The next thing we'd have to do if we really wanted to do something is try to figure out an experiment where only methane changed and O2 didn't change and see what happens to our rate. We could do the mathematical method. We could do it the logic method. Let's go ahead and do it the logic method. And the reason I'm doing this is in order to solve for the rate constant K, because I said we would. And so let's go ahead and do that. So what are we going to do? We're going to look at those first two experiments, because remember our O2 didn't change much, but our CH4 did. Our CH4 went from about 0.05. I'm going to round that next one to about 0.1. So what did it do? It just about doubled. And what did my rate do? My rate went from 4.7 to 9.1, which is just about doubled. And so logically, what I would write down, not just 2x, 2x, don't write that on a test. I want you to have a sentence that says, because the rate went up by a factor of 2 when CH4 concentration went up by a factor of 2, it is first order in CH2. So if I scroll back down here, I'm going to change that M to a 1, and I get rate equals K times the concentration of CH4 times the concentration of O2 squared. In order to figure out the rate law, I pick one experiment on a test or quiz. In lab, I do all of them, and I average out, and I do some statistics. So I'm going to go ahead and just do it this way. I'm going to pick experiment 1. Why? Because that's the one most people pick. 4.7 times 10 to the 4th molar per second is equal to K. Notice, I also meant to say this a long time ago. As soon as I type in a number, I'm using parentheses. When I'm talking about the concentration of as a concept, and I've got, a molecule in there, I use the square brackets. But as soon as it's a number, it's parentheses, not square brackets anymore. 0.0510 to the first. Oh, don't forget your units. Molar to the first. And O2, 0.0203 molar squared. This is just some math. So we're going to take 4.7 times 10 to the minus, or sorry, 10 to the positive fourth, sorry, and divide by 0.0510 times 0.0203 squared. And we're going to end up with units of 1 over molar second, 1 over molar squared second, sorry. If you don't know how I did that, you actually work out the units, and you should see it. I'm going to type that into my calculator. I get 4.7 times 10 to the 4th divided by 0.0510 divided by 0.0203 squared, oops, wrong button, squared, and I get that K is equal to 2.24 times 10 to the 9th. We decided that was per molar squared second. What is a per molar squared second as a unit? I don't know, you don't know, it's okay, nobody knows. But that's our value. That's what we'd use if we were trying to calculate the rate of any other of these reactions if we knew the initial concentrations. That rate constant should be constant across all times we run this reaction at a given temperature. And it's useful that way. So there we go. We calculated the value of K, a very large K, which we expect for burning something. Again, I made up this data. And then we calculated its first order with respect to methane, second order with respect to oxygen, which makes it third order overall. And that took us 26 minutes. All right. Good luck. Thanks. Bye.